as a vibrant platform where academicians, industry professionals, engineers, and researchers from diverse fields, ranging from technology and healthcare to management and emerging sciences, join hands, discuss, explore, and innovate in the dynamic world of machine learning algorithms. Over the next 2 days, we will delve into exciting topics including artificial intelligence, neural networks, predictive analytics, supervised and unsupervised learning, computer vision, pattern recognition, healthcare applications, and cybersecurity. Special workshops on computer vision and healthcare industry 5.0 and computational intelligence will further enrich the expertise. Now, let us begin our journey with the virtual tour of Chitkara University. Can we have a video, please? bring together such a vibrant community of researchers and professionals, united by a shared passion for innovation, research, and knowledge exchange. The spirit of shared knowledge is the very essence of what we hope to achieve in our upcoming sessions. Now, I would like to invite Dr. Sagar Jadeja, Associate Director of Research at Chitkara University's Curine at for welcome address. With over 11 years of experience of academic expertise in analog system design, embedded systems, RF circuit design, and antenna engineering, complemented by 6 years of rich industry experience with global leaders such as Texas Instruments and RS Components. At Chitkara University, he leads several government-funded projects, serves as the editor of the Curine newsletter, and the convener of 2 international conferences, deriving innovation and collaboration. He has also co-edited 2 books published by Springer, reflecting his strong scholarly contributions in computing, data analytics, and secure networks. We are delighted to have you here for a welcome address.
Good morning, everybody. It is my true privilege to be a part of this prestigious conference and to deliver a welcome address in this inaugural ceremony. So, thank you for the opportunity. At the onset, I would like to congratulate Dr. Abhishek, Dr. Pradipta Sarangi for and their entire team for putting together such a nice conference. It is the second edition of ICMLA. So the conference, which is very, very meaningful in today's time, focusing on machine learning techniques and their applications. And congratulations to you for bringing together such great, speakers who are going to talk about various issues and opportunities and applications related to machine learning techniques and algorithms. I would like to acknowledge their presence of our keynote speakers who are going to speak in the various sessions over this period of 2 days. We have Professor Anirban Sen Gupta from IIT Indore, Professor Gaston Papini from University of Trento, Dr. Ranjan Jha from IIT Patna, Dr. Anuradha Kar from Ivan City School of Technology, Business and Society, Paris, Dr. Aditya Nigam from IIT Mandi. So we are truly privileged to have such stalwart in the field of AI and machine learning who are going to interact with us, and they are going to talk about various things, including applications of machine learning in healthcare primarily, and then application of machine learning in estimating physical systems. Then there are talks on various attacks on machine learning accelerator and how to mitigate those attacks. So these sessions are going to be really, really insightful. I'm sure about that. I would also like to welcome all the delegates to this inaugural ceremony and to this conference. Thank you for contributing your good papers in the conference. And the papers that are going to be presented are going to be published in a prestigious CCIS series of Springer Nature. So that is again a very good publication platform. So congratulations to all the authors whose papers have been selected for publication, and I wish you all the best for your presentation. I'm sure we are having different session chairs in the delegation today in this forum today in the inaugural ceremony. So welcome all the session chairs, and we are truly grateful for your support. I'm sure most of the session chairs are also the reviewers who have reviewed papers in the conference, and so thank you for your support, and thanks to all the reviewers who have supported in reviewing the papers in the conference. I would like to talk about 2 important things that are on my mind in this welcome address for next 5 minutes, that the time that has been allotted to me. One is that I myself am a part of various conferences in the capacity of publication chair, convener, Then I have been the editor of several, special issues in journals. So I would like to talk about my pain areas, and which I'm sure are the pain areas of a lot of you people who are dealing with the conferences and publications. And since this is a community of researchers who are, publishing, and whose responsibility is to ensure that the ethical publication should happen. So this particular thing will be important for all of us to, understand and appreciate. So today we talk about AI, right? AI being omnipresent in every system, every application, every walk of life. So the publication domain is also not, untouched by AI. So we see a lot of AI being used in the publication processes, be it used by authors for, paper correction or paper drafting or finding ideas, and or be it is used by reviewers for reviewing papers and things like that. So I would like to impress upon all of us that uh, in the publication domain, I'm going to talk only specifically about publication domain. The use of AI should be very, very ethical and very, very judicious, judicial use. Why? Because when we receive papers in the conferences, we see sometimes the papers are totally AI generated, and it creates a lot of, a sense of hurt among us as publication chairs and conveners, that authors these days are taking this easy route. And trust me that these days there are so many tools available, which can tell you that the papers are AI generated, and there is no way your paper can pass through those barriers. So we should be very, very careful when we are submitting our papers, uh, that the AI should be used in an ethical manner. That is one thing. The other pain area that we have is in the review process. So I see a lot of my colleagues, when I say colleagues, all of you are researchers who are working in different institutions, right? Some of you may be research scholars. So I'm sure you must have served as reviewers in various conferences and for various journal publications, right? So I have seen that these days reviewers are also using AI to generate reviews. That is not a very happy situation. We, as it is our responsibility as ethical researcher to promote, ethical research. And when AI is used for reviewing papers, it is very difficult for us as, conveners and publication chair to, take decision on those papers and send the AI generated reviews to the authors. So it is my humble request to all of you, and I mean all of us, that uh, uh, when we are doing this task of handling publication processes, we should be. I'm not saying we should not use AI tools. We should be using them, but we should be using them in an ethical manner, right? So this is one area I wanted to touch upon. Uh, Other thing is that at Chitkara University these days, we have a very strong focus on organizing state of the art conferences. So very recently, Chitkara University, Himachal Pradesh organized another conference which was held in the month of July, right? It was a conference on computing, analytics, and networks. In total, Chitkara University at both the campuses, we are doing close to 15 conferences in the year. Like in 2025, we are doing close to 15 conferences. We have one conference coming in the month of October, then we have one conference coming in the month of November, then there are two conferences in December. So, what I'm trying to impress upon the research community is that Chitkara University has a mandate to organize state of the art conferences which benefit the community, the research community, in the best of its
Hello?
ability, right? So we invite you
Uh,
to submit papers in our conferences, in all our conferences, and
uh,
benefit from it. uh, we have something called
uh,
as a department called Chitkara University Publication, where we are running 5 journals in that particular under that initiative, and uh, we invite all of you to be part of those journals. in the capacity of maybe authors or maybe collaborator. If you want to do special issues in those journals, we invite you to, partner with us. So if you visit the website of this particular conference, ICMLA, you will see there's a page on Chitkara University publications, and you can get the contact information and all those things. So I'm going to talk about these journals. There are 5 journals that we have. One is a journal of multidisciplinary research in healthcare. The second one is a journal of pharmaceutical technology research and management. The third one is journal of technology management for growing economics. And the fourth one is journal of issues and ideas in education. So these 4 journals are Chitkara University's journal, published by Chitkara University. Then last year in the month of September, we uh, we acquired one journal from Springer Nature. This journal is published by Springer Nature, but it is a Chitkara University owned journal. It is Journal of Transformative Technologies and Sustainable Development. So this is a Scopus Index journal, and it's a diamond open access journal, meaning the article publication charges is being paid by Chitkara University to for those articles which are selected for publication and they are of top quality. So we invite you to please explore these journals and try to submit articles in all of these journals. They are good journals. In fact, for JTTSD, Journal of Transformative Technology and Sustainable Development, we have given a privilege or this option to all the conference organizers of Chitkara University that they can submit top papers of their conference to this journal for consideration, and it will be published as open access. So for example, I understand that this particular conference is going to have 40 paper presentations. So I would like to inform Abhishek sir and Pradipta sir, and I'm sure they already know about it, that you can send, top papers from your conference after the paper presentation, whatsoever are the top papers, for consideration in the Journal of Transformative Technology and Sustainable Development. And if those papers are submitted, let us say by September 30th, we should be able to get them reviewed in a month or 2 months time and get them published as a open access papers in the journal, provided they are extended work of the work that is being presented in the conference. It should not be the same work, obviously. It should be extended work, both in terms of experiment and in terms of novel contribution. So this is what I wanted to talk about. Thank you very much once again for the opportunity. I'm delighted to be a part of this conference, and all the best to the conference organizers, and all the best to the delegates, and have a good 2 resourceful days of ICMLA 2025. Thank you very much.
Thank you so much, sir. Thank you for your kind words and information. And so, dear participants, today's inauguration sets the stage for the intellectual journey, and it is our honor to begin with inspiring words for our invited dignitaries. Before that, I would like to present a vote of thanks. This journey of growth would have been not possible without the visionary leadership of unwearying support of our chief patrons, Dr. Ashok K. Chitkara, Honorable Chancellor Sir, and Dr. Madhu Chitkara, Honorable Pro Chancellor Ma'am. Their commitment to fostering academic excellence has been the guiding light for this conference, and we are sincerely grateful for their continued inspiration. I also extend my warm regards to Dr. Rajni Sharma, Honorable Vice Chancellor Sir, and Dr. Meenu Khurana, Honorable Pro Chancellor Ma'am, whose vision continues to guide our university in the pursuit of excellence. Also, extend my thanks to Dr. Sagar Juneja sir for continuously supporting and guiding us with this conference, and all the organizing committee members. Thank you so much for this beautiful conference. So, I would like to invite, and it is my pleasure to introduce rather our first keynote speaker, Dr. Aditya Nigam, Associate Professor in the School of Computing and Electrical Engineering at IIT Mandi, Himachal Pradesh. Dr. Nigam's research expertise lies in the deep learning and its application in biometric, including palm print, knuckle print, iris recognition, and advanced multi biometric systems. He's highly influential researcher whose work has earned nearly 2,000 citations, reflecting his impactful contributions to the scientific community. His academic excellence is recognized globally with an impressive H index of 24 and an I-10 index of 58, underscoring his scholarly influence. Today, he will be speaking on the very timely and significant theme of machine learning in healthcare. We are truly delighted to have you, sir. Over to you now.
About medical imaging and the research that we are trying to do here at IT Multi, few of the areas into which I am working on. But before going to talk about the areas into which I am working and the time that's been given to me, within that, if I want to finish it off, then I need to be really quick. So I will try to finish the things in time. And my starting point is going to be like I'm going to talk about initially, say, uh, very top level understanding of deep learning and all within 2 to 5 minutes. That usually you have a data. Suppose that this is my database into which I am having a data, say X, and I ask multiple questions to this data and convert it into a feature vector. And this feature vector can actually be an X1, which is going to be a multidimensional vector, say X1, X2, X3, and so on, maybe X2, XD. So essentially, my data becomes a d-dimensional vector. Now, given this d-dimensional vector, now suppose that I have got this d-dimensional vector, what I can do is that I take this d-dimensional vector like this and have a single neuron which is going to take all of these things coming into it. This is our W1, W2, W3. So this is my X1, X2, XD, and this is going to be WD. And along with that, you are having a bias which is X0, which is equal to 1, and the corresponding weight Wi. So basically, this is the Wi, the corresponding weight that we are going to learn, which is going to be W0. And essentially, this neuron is not going to do anything other than summation Wi xi. This is a nutshell a single neuron is going to do. After that, we activate this neuron using some activation function. Now the point is that instead of having a single neuron, if I have more than one neuron, and then if I have more than one layer, and when these layers started to become deep and deep and deep, huge amount of layers, and in each and every layer you are having huge amount of neurons, then actually it becomes a deep neural network. Now there are other topologies in this neural network that initially you have input layer, then you have the second layer, then you have the after each and every layer, the feature size we keep on reducing, doing max pooling and all. And at some point of time, we somehow can also do the upsampling. So this is actually downsampling which is happening. Then you can do upsampling as well. And then in this way, at last, suppose that X is going in and some X hat is coming out, we train this type of network using X minus X hat. And this essentially become the initial, or maybe the first part actually become encoder and the second part become decoder. So you have got an encoder-decoder network, and several times this encoder-decoder network, if it is being trained by a loss function like this, because the same X is being shown to the network feature vector, that the bottleneck feature that you are getting over here, and from that you explode, or one can say keep on extending or making it bigger and bigger and making it to the original size, and then you expect your network to reproduce the same thing again. That is why several times this is called as auto encoders. So you have got, fully connected network in which single neurons are being there, then multiple neurons are being there. And then instead of having a fully connected network, fully connected neural net, you can have a convolutional neural network in which instead of applying multiplication operator and aggregating all the inputs, instead of that, you just localize the effect. And if you wanted to know something about this pixel, you only decide that given a particular neighborhood, how can I decide that what is there inside this pixel, what is happening, then we can localize it within a particular neighborhood. That's called as convolutional neural networks. And given this type of neural networks, we started to work like, we started to say that initially we decrease and make it a small bottleneck, and then we increment it again, or one can say deflate and make it bigger again, and from X we make it X hat, and then train my network in this way, back propagate. Then we assume that this is going to be seen as a auto encoder type of network. These are different topologies. In just a very nutshell, I just wanted to cover so that you got a glimpse that what type of things that I'm going to cover in the second part of my talk, that what are the areas, the work in medical imaging that we have done. And you have got, suppose that you need to, do a image segmentation, in which suppose that you are having an image in which certain things are being here, and you want your network to actually predict that if I show you an image like this of a cat or a dog or something where here is the cat, you need to somehow tell that, okay, this is the area, this is the region into which there is the cat. So the segmentation, image segmentation, or image object detection or segmentation, or maybe different types of uh, one can say uh, one can say different types of problems into which you need the output which is also of the same size. Input and output, both of them are going to be of the same size. Then you need a network which is an autoencoder sort of network, or maybe an encoder decoder sort of network. And from here, everything started to move in a slightly varied way, in which they will started to say that instead of only doing discriminative modeling, in which you just say that given this data, it belongs to class A or it belongs to class B, which is essentially doing the discrimination, they started to talk about generation. So how can I generate new data? From autoencoders, you can generate new data. How? I just have shown that, okay, this is the bottleneck over here. Instead of so X will go in, Z is the bottleneck, X hat is going to come out. And instead of training this network in this way, we started to train it like this, that instead of having Z, we started to say, don't tell me what is that Z. Instead of that, can you tell me the distribution from which these Zs or the bottleneck vectors are going to be coming from? So we say that this is the mu Z and the sigma Z. And given that mu Z and sigma Z, if I can sample things from here and show it to my decoder, again, this is your encoder and decoder. So again, I will say that, okay, that given the distribution by which my Zs are coming from, I can take that and show it to my decoder. And then, given that decoder, I can say that whatever is being generated, how close it was as the given thing. So this is also a type of encoder, but this is called as variational autoencoder. And from this variational autoencoder, if I take decoder over here and encoder over here, decoder over here and encoder over here, what does it mean? Then I sample something from random space, show it to my decoder, which is now become a generator. And whatever I have generated, these images which are being generated by my network, I make certain images coming from the real data set, certain images which are actually being coming from the fake data set. And given real and fake data set images, I make a batch and ask my discriminator type of network, which is essentially going to be a type of, one can say, classification network, which will take an image and decode it into a smaller vector and then apply a classifier over here. So this will become generator. This is being several times being called as the discriminator. And now you train your network using an adversarial loss. It's just a quick brief that these type of networks are being called as GANs. And finally, these GANs are also being outdated, and we started to use something which is called as diffusion modeling, in which instead of learning the distribution, instead of learning the latent or maybe the distribution of real or the fake data, real data X, we started to say that no, I'm not going to train my network or learn this distribution. Instead, I started to learn how to diffuse and how to denoise my data. And generation via denoising. Generation via denoising. So how can we generate via denoising? So I take an image and add some noise into that, and then it will become, so this is I1, that's a real image. This is I2. Say this is slightly, I add noise into it, it will become I2. I add more noise into it, it will become I3. I keep on adding noise, keep on adding noise. At some point of time, this will become completely noise, and then I started to do denoising instead. Now this denoising is going to be learned, and noise addition was not being learnable, because anyways noise addition is a simple process. Image processing, you just take and multiply a Gaussian kernel and keep on doing that. So this denoising, learning of this denoising, how can I generate I3 from maybe I4, is a thing our network has to somehow learn. That becomes the new paradigm, which is essentially being several times now in the picture, and everyone is using all this, things which are being generated via AI, images and text and everything that you can see. There is something common into them, and that is a neural network, which is being trained using denoising neural networks. So denoising neural network, which are essentially being technique, is being known as diffusion model. With this background, let us understand that, okay, you have a CNN, you have an RNN, LSTMs, you can have autoencoders, you can have VAEs, you have GANs. So basically you have discriminative modeling, and then you can have generative modeling. Given diffusion model, diffusion, or one can say discriminative modeling as well as generative modeling, what are the things that one can do? So certain type of work that we have done is the first work that we have done. It was being published in 2020, very old paper, one can say, but still it is very relevant. And at that point of time, just transformers actually came on. And what we have done is that, given an image of an X-ray or something, and some ground truth for certain images were being given. So radiology report was being given. MTI tags, these are the tags which are being somehow been also given along with the data sets. These are some of the important key tags which are being given by the medical expert from these medical terminology, radiology report. And our purpose is that, given this input image, how can I take this ground truth and train my networks in such a that whatever be the ground truth, similar to that I started to do, and generate that X-ray report generation. So from the image, automated X-ray report generation is the work that is being done. And this is the way in which, so initially X-rays were being given. Onto that we apply certain, some object detection network, so as to figure out where is the lung. So once you have got the lungs, then we take that, and we have a abnormality detection network, which is somehow trying to see that what is the area and is there any abnormality. And if there is some abnormality, then we try to tag, okay, so there is some abnormality. If it is normal, then we will go directly. Otherwise, if it is abnormal, we can show it to our tag classification, because we also know that MTI tags, what are these tags which are being there. So can I somehow figure out that what are these, given this image and this region, what are the tags to which it's actually belonging to, because these tags are going to be utilized for my report generation network. And later we have findings, we have impressions, both of these things are going to be generated from. So there are three networks. One was a chest X-ray detection, then abnormality detection, then tag classification. And finally, once you know that what is the tag, where is the X-ray, and what type of issues that are being reported, or one can see, we have utilized another network, that's the report generation network, which is essentially a transformer network, which is going to say that what's the finding and impression, and what's the final report coming out of that. This was one work in medical imaging that we have done. The other things, certain things we started to work on, was the MRI imaging. And as we all know, MRI, everyone is aware, but there are two other modalities as well, and these are the very recent upcoming modalities. So nobody right now capture fMRI and DMRI most of the time, because both of them are right now under very initial stages, and most of the time being utilized for research research purposes. But MRI is the thing everyone actually uses. So MRI is going to be seen something like this. fMRI is MRI is going to say that structural connectivity of the brain. So if you have a brain like this, then this structure, how they are actually being connected. fMRI is actually the functional connectivity of the brain, which essentially say that if I have a brain, I stimulate it using different things. So suppose that you are listening to a music, if you are watching a movie or something, then these are the regions which are active. And if you do something else, then some other regions are active. And how this activity is going to functionally connect different regions in the brain. So fMRI is a functional MRI. Several times it's being used to diagnose different types of disease. The third modality is the DMRI, that is the diffusion MRI. This diffusion is different than the diffusion process that I was talking about. This diffusion is the diffusion of the water molecule. So suppose that if you have a piece of thread. So suppose that you are having a newspaper and an ink got dropped, and you can see that it is equally dispersed in all possible direction. Why? Because उसमें कोई direction नहीं है. Now suppose that you have a thread, this is a thread, and if you have got a ink molecule being placed onto this, so it's not going in each and every direction, it will follow this path. The assumption behind the MRI technique is that within the brain there are some fibers, there are some neurons which are having a path going something like this, and if there is a water molecule over here, it's also going to follow the same path, the way in which the water molecules are following. So that is the process. That is why it is called as diffusion of water molecule. And if we can compute the water molecule diffusion in each and every voxel of a brain, then we can somehow figure out the DMRI of that. The DMRI is going to tell something very important, and very soon I will see. I will talk about what are the things that can actually be done using DMRI technique. But by the way, these are the structural connectivity, these are functional connectivity, and this is a much more fine-grained structural connectivity. This was actually telling that the regions which are being connected, this can actually tell that how this region is connected to this via different fibers or neuronal connections. Okay. So MRI equation technique. So you have a single Tesla machine, 3 Tesla machine or 7 Tesla machine. Inside that you go, and then we acquire your data. And it is essentially that, suppose that this is your one brain, and I can watch your brain in one direction. Right now I am watching. So in MRI, we watch the brain in only one direction, and all these slices are being cut. And for each and every slice, we have a particular, spatial location, that okay, each and every this brain can actually be seen as a 3D, and within this 3D we are having a voxels like this. So individual voxels are there. Now I take a single voxel, and this single voxel is essentially over a particular this single voxel is over a particular slice of a brain, and given this slice and this voxel which I have shown over here, what is the direction into which I am looking? Now suppose that I am looking in this direction. So MRI sees one single 3D structure, which is essentially our brain in only one direction, and we dissect, or one can say apply different gradient maybe in this direction, so that each and every slice 1, slice 2, slice 3, slice 4 and 5, and within each slice, each and every voxel, we started to get the corresponding frequency as a frequency signal, as well as the phase encoding. So the frequency and the phase encoding for each and every voxel got stored in a particular map, several times being called as a special frequency domain. We save everything into a single K space, and this single K space is essentially each and every voxel's corresponding phase encoding and the frequency encoding. And when you got all that stuff, essentially you can utilize all that stuff. And given that K space, one K space is essentially watching a brain in one direction, and all possible one can say the voxels, and you have got all that information, and then we do the inverse Fourier transformation and finally get the MRI. This is the way in which, in a very broad sense, in 2-3 minutes, what I can explain about K space. But K space looks the brain into one direction, but each and every voxel of the brain is essentially somehow being computed. The signals are being computed. And this is the thing that I was talking about, that within every brain, you can say that there is the white matter and the gray matter. And within the white matter, you can see this is the structure. Now, given this structure, you can say that something is connected like this, something is connected like this, something is connected like this, or maybe some things are connected like this. Now, this depends upon that this white matter is having different types of neural connection. And these are the neurons which are going to make all that stuff. So given this thing, can we figure out that how these connections are being done? That's the very fine level structural connectivity that is essentially being required if you wanted to diagnose that certain things are working in the brain, certain things are not working in the brain. Traumatic brain injury has happened, something has happened. How can you figure out that what are the fibers which are active, what are the fibers which are not active? So given that, so as I have said that the single brain is essentially going to, sorry, single direction. If you watch, then you are going to have a static images of certain brain, and one brain MRI essentially going to do that. But instead of that, if you can watch your brain in 2, 3, 4, 5, so 6 different direction, if you can see, which is essentially meaning that brain is a 3D structure. Instead of watching only in this direction, I can watch in this, I can watch in this, I can watch in this and this and this. So if you watch them, these brain into multiple directions, then it is started to become a diffusion tensor imaging. And later you can say that instead of 3, you can have more directions, and you can have multiple uh, multi Tesla imaging. So which essentially mean that instead of only having a 3D imaging, one can say that I can change the magnetic field. So I watched my brain at 1.5 Tesla. I can watch my brain at different magnetic fields and in different directions. So if you can see at different magnetic fields and with different magnetic field as well as multiple directions, then only you can figure out that for each and every voxel, how much amount of water is going to flow from one voxel to another voxel. And this technique is essentially, so you can have a magnetic strength is going to be changing, magnetic the gradient direction can change, as well as the sampling technique can also change, and depending upon that, the diffusion time is also going to be incremented. But with this incremented time, you can have a far more useful structure about a brain, which is essentially going to say that, okay, here you can see that this is the brain, certain regions, and these are the connection neuronal fiber of a particular, suppose that corticospinal tract in the brain, how this is being fanned and being connecting different brain regions. If you can do DMRI, then it can actually be done. So into this, we have done multiple, contributions, and one of them is that. So now in this way, each and so K space, as I have said, that one single K space can generate one direction in which you can see the brain, and this is one direction, this is another direction, this is third direction, fourth direction. So instead of having one direction within one shell, this is one shell of my magnetic field. So within one set of one magnetic field, I am looking my brain in multiple directions. Then I apply second set of field and the third set of field. So I am having 2 or 3 different magnetic field variations are being there, and for each and every variation in the magnetic field, we are looking brain. And now you can see that instead of having a one diagram or one MRI, instead of that we are having multiple brain images. And given this multiple brain images, we can somehow estimate the 3D structure, which is essentially telling that how a single brain fiber is going from one direction or one connection to, or one brain region to another brain region. This is the thing which is essentially being done in the case of DMRI. And we have somehow done single shell to multi cell conversion, in which suppose that single shell means that I am having only one magnetic field. From one magnetic field, how can I predict the higher magnetic field signals? And that is the thing that we have done in this paper, in which again, as I have said, that we have utilized different types of VAEs and GANs. And now you can see that this is the fiber structure. That's the thing that we are interested to figure out, that certain fibers are starting from here and ending over here, certain fibers are starting from here and ending over here. And just think about that, there is some surgery which is supposed that about to happen, and doctors are looking that, can you please tell me that what are the regions which are being connected by these fibers, so that I can decide that if I cut the brain, certain fibers are definitely going to be removed. And the fibers are removed, then you need to figure out that what are the fibers that you can remove. You don't want it to remove very critical and important fibers. Now suppose that some fibers are there which are related to your brain, within your brain they are related to your eyes and your vision. You don't want to cut that, but instead of that, you can remove certain fibers which are just going to say that your left and right balance is going to be misaligned. So how can we estimate such type of such type of parameters, so that they can actually be essentially utilized, so as to give you a very fine grain decisions and very critical decisions during the surgery that you need to take. The other thing that we have done is that 3T Tesla and 7T Tesla, 3T Tesla and 7T Tesla, how can I convert my data from 3T to 7T? Can I convert my data from 3T to 7T? As I have said that 3T is most of the time, still 1.5T is available, but in good radiology centers, you can have 1.5 or maybe 3 Tesla, but 7 Tesla is never ever available in India. Very few centers are there. So is it possible that can we utilize machine learning and deep learning techniques to somehow convert even 1.5 Tesla to maybe 3 Tesla, and from 3 Tesla we can make it to 7 Tesla data when only data is being captured using 1.5T or maybe 3T data? So this was also another contribution into which we have somehow said that you can utilize a selection GAN sort of network, which we have adapted in such a way so that from this 3T Tesla to 7T Tesla data can actually be realized with a certain amount of, within a particular amount of error limits. As I have said that once you have got all this, 3T data to 7T data and high resolution data, why do you need this data? You need this data so as to figure out that how these neurons are being connected here and there within this white matter. So essentially we need to do tractography, and once we do tractography, you are going to get, your brain can actually be seen like this, in which individual voxels are being connected, and something like this. These are the neuronal fibers which are being connecting one region to another region. How can I track them? So this is this problem statement is now being essentially called as the tractography, human brain tractography. How can I one can say track that if you give me a point over here, there need to be a technique which can start and can finish over here, which is going to tell that how can you track a particular brain, within a particular brain, different fibers which are going from place A to place B. And for that we also have generated our own neural network, which is a reinforcement learning RL based neural network, which is essentially a tracked RL former, which is a tracked specific RL based policy learning network and decoder only transformer model, which is essentially going to talk about that given this all DWI data, as I have said that DWI data is nothing but for each and every voxel, how much amount of water is going and in what direction. That is why it becomes tensor. So if I take a voxel, and for every voxel, I will say that my data is moving in maybe 3 direction or 4 direction or whatever be the different directions in which the maximum amount of water is flowing within a particular voxel. And if I say that, that becomes the DWI data. Now, given this DWI data, which can actually be in 2-dimensional, can be very simply projected like this. Now suppose that this is my single voxel, this is suppose that my single voxel, this is suppose that my single voxel. I am saying that the direction into which my network, the direction into which water is flowing, the direction to which the water is flowing, the direction to which the water is flowing, and so on. Now, if somebody can give you this, tractography means that if I give you a seed, you need to know, if I give you a seed over here, you can say that, sir, there is some direction like this. So this is the tractography algorithm. Suppose that if I give you a point like this, you may say that, okay, it can go this way. This is a box. This is a track, or this can be a particular fiber. So this is called as tractography, and this is right now in 2D, but essentially individual voxels are essentially in 3D, and for each and every voxel you got a tensor. Now given a huge amount of voxels, and for each and every voxel different tensors, how can you figure out that what is the direction into which one should have to move so as to get a longest maximum length fibers, which can actually be representing the structural connectivity of the human brain. So this is, RL based policy that we have learned, which will start from a particular seed and keep on moving in the direction within the neighborhood. It just try to see that what is the most aligning direction for whatever I have seen so far. So now previously was going like this, and at this location, you see that I can move in this and this and this and this. then it will discard this, discard this, discard this, and try to move in this direction so as to align as much as possible in the previous direction. So this was something in which this was actually their loss function of RL algorithm, in which we just see that what is the alignment of the uh, fibers that we can have, which are going to connect you to your previous direction. So that's the our last year paper, in which we have shown that if you can do it in this way, these are the generated things. This was the suppose that the ground truth, and this was the generated tracks from our algorithm. Suppose that this is the ground truth and this is the generated tracks from our network, and we have shown that okay, not exactly same ground truth we can generate, but we have shown that using such type of RL based algorithms, human tracks, human brain tractography can also be done, which is a very promising new upcoming direction in the field of brain tractography. So given this, one can say that this type of brain actually got converted into this, in which now you can figure out and say that okay, these are the region. Now suppose that there is a tumor over here, suppose that there is a tumor over here and you need to go, then you may probably go it like that, you may probably go something like this, but you don't want to go something like this because this may be a very important fiber track in the line and you don't want to cut that or touch that. Certain other ongoing works are that given gallbladder data, so gallbladder ultrasound images, if we can gallbladder, we need to figure out that this is the gallbladder and the corresponding what is the wall thickening, different other parameters one can see, so that we can figure out that whether these videos which are being given to us, they are having certain cancerous information or not. Otherwise, so cancer detection gallbladder can actually be, ultrasound gallbladder data can actually be utilized, and there are several publicly available such ultrasound gallbladder data sets available. Similar to that, certain breast cancer images and data sets are also publicly available, on to which our students are working on. 1 minute left. So I'm done with this. If you have any question, you can ask. I was very fast because I just wanted to cover certain things and also give you the background which is being required. I hope you may have got some sense that I wanted to cover. Yes, I'm done. Thank you, madam.
Two, you're a distinguished professor in the Department of Computer Science and Engineering at IIT Indore, Madhya Pradesh. Professor Sen Gupta is globally acclaimed researcher with more than 330 publications, 16 patents, and 6 books, establishing him as a global leader in computer hardware and architecture. His pioneering work has earned him recognition as an ACM India eminent speaker, and he is a proud fellow of the Institution of Engineering and Technology, the British Computer Society, and IETE. He has been honored with several prestigious international awards, including the IEEE Chester Cell Memorial Award, and is consistently ranked among the top 2% scientists in the world by Stanford University. Congratulations, sir. Currently, he serves as an editor in chief of IET, Computers and Digital Techniques, the first Indian scientist to be entrusted with this distinction. Please join us extended a warm welcome to Professor Anirban Sen Gupta. I hope
to give a talk on Trojan attack on machine learning accelerators. I would like to congratulate all the organizers involved in this initiative and the university authorities and the other people. Thank you so much once again. So I'm going to speak about Trojan attack on machine learning accelerators, and it is going to touch upon a new dimension of machine learning, which most of the people are not really aware of that much. Although there are a lot of developments going on across the globe on such pertaining issues. So let me talk about the broad perspective of how these security vulnerabilities can be exploited by the hackers during the design of machine learning accelerators, specifically in the context of convolutional neural networks. My talk will also highlight about the different ML accelerators from the academia and the industry, as well as the different design stages where the Trojan attacks can be launched. I will also give you a glimpse about the existing literature on how the Trojan attacks can be injected, triggered, and exploited to perform various kind of payloads. And finally, we'll discuss certain mitigation and detection techniques. As we know, there are certain key machine learning algorithms like linear regression, convolution neural network, support vector machine, and so on. And most of these techniques rely on data intensive cores to perform certain forecasting, data prediction, and classification. So, for example, CNN is used in various applications like face recognition, object detection, image segmentation, and so on, while LR is used for data estimation and prediction in smart systems. Now, most of these ML algorithms, they have probabilistic models which perform extensive computations on the input data for tasks such as classification and prediction. And in the context of CNN, it can have different layers like convolution layer, pooling, flattening, fully connected layers, and so on. It would be ideally great to have a dedicated coprocessor or an intellectual property design that can cater to these data centric applications, because most of these applications require huge data or data crunching algorithms to perform certain inferencing. So these dedicated computing platforms could be implemented as FPGAs, or they could be implemented as application specific integrated circuits, which are nothing but the fabricated version of the IP designs. So I'll talk about how these IP designs can be exploited via a publicly known framework, which is known as high level synthesis. It's a widely known framework used for design of several accelerators, including machine learning accelerators. Now, some of the real life examples of ML accelerators could be NVIDIA Deep Learning Accelerator, which is very widely popular. There's one from Google, which is very close to Tensilica processor. And also there are several other academic initiatives where these ML accelerators has been made, including one from my IIT, which are published extensively in IEEE transactions. So as you can see from the figure here, that the ML accelerators can be implemented in either of the three possibilities. One is to have a coprocessor or usable IP. Second is to have a ASIC, and third is to have an FPGA. Now, in the design of NVIDIA, which is a CNN-based hardware accelerator, the side channel leakage attack can be performed, okay, which is nothing but leakage of sensitive information such as power and timing to recover important crucial informations like neural network parameters like kernel size, number of filters, and so on. Okay. The other option could be you can bypass the encryption using a multiplexer switch, where you can provide the plain text here as an input and the encrypted text here. Okay. And the switch could be controlled by the attacker using external antenna to bypass the encryption and provide the plain text at the output. Some other forms of Trojan attacks on machine learning accelerators could be something known as NBTI, which is negative bias temperature instability stress, where an attacker tries to accelerate the aging process of the ML accelerators, okay, by exploiting the NBTI stress as a hardware Trojan. The other option could be to employ performance degradation Trojan attack, where secretly a Trojan logic could be inserted during the scheduling phase of the ML accelerator design. And that can also result into something known as battery exhaustion attack, where there could be unwarranted amount of power consumption than required. Some other forms of hardware Trojan attacks could be denial of service, where you can stop the output from being produced suddenly, causing abrupt disruption into the design flow of the data path. And there have been literatures that have covered topics on this. For example, these three specific references are all based on Trojan attacks on machine learning accelerators, or in general, any sort of accelerators that are widely used in image and data processing. In this figure, what we see is that we can take the input in the form of a C code or any other high level code of the application. or the transfer function of the machine learning algorithm. And it will then pass into the design process, which includes scheduling, allocation, and mux interconnect design phase. And finally, it produces the accelerator design. So this is a general process of how ML accelerators can be made. And after that, we can employ HLS, okay, where HLS is mostly the framework used for designing the ML accelerator. An attacker can maliciously leverage or exploit HLS by compromising the CAT software. Okay, so for example, the CAT software that exploits HLS can be misused rather or maliciously used to perform battery exhaustion Trojan attack, data damage Trojan attack, performance degradation Trojan attack, and denial of service Trojan attack. All of these are possible. Interestingly, an attacker can even launch multiple of these attacks at the same time. And as a result, what happens is a compromised RTL. So RTL is nothing but a registered transferable description of the ML accelerator design. Okay, so ML accelerator design means if you really want to make an accelerator in the form of IP, FPGA, or ASIC, you would need to describe it in the form of RTL, which is registered transfer level. And RTL is the output of HLS, which is the framework that a hacker or an attacker can actually maliciously use in order to inject Trojan into the design flow. The lower half of the slide explains about the design flow. So suppose you have the C code or transfer function. So this is basically talking of the convolutional layer in CNN. You can make it into an expanded transfer function. And then from there, you can derive the data flow graph, which is shown here. So this is pixel wise. So the output here is for the first pixel after convolution operation is performed. When you basically try to perform convolution between the input image and the filter kernel, 3x3 or 5x5, depending on what is the requirement. And then the CNN accelerator is produced in this form, which is nothing but the data path of the convolution layer. Now, since convolution layer has to do data crunching, okay, between that 3x3 matrix and the kernel filter, okay, 3x3 as in like the size of the filter kernel and the input image, which could be 512 cross 512. So it needs to do a lot of computation mathematically. So therefore, it becomes a data crunching or power hungry application. And that's why we need an accelerator to do that. So CNN accelerator basically is responsible for producing that specific function. Now, in terms of the different types of adversarial payloads, as I had mentioned earlier, that Trojan attacks can have different payloads. So payload basically means what is the effect on your ML accelerator? What is the effect on your AI accelerator? So in terms of the effect, the payloads can be of various forms. For example, the payload could be denial of service. Denial of service can be performed by DOS hardware Trojan. Okay, we call it DOS, denial of service hardware Trojan. The performance degradation means whatever timeline is expected to produce the respective output, it adds extra propagation delay to the computation, resulting into performance degradation. So that kind of Trojan is called PDHT. That is also equally applicable for ML accelerators. The next is called data damage hardware Trojan. Now, data damage hardware Trojan means it is responsible for damaging the data, corruption of the data. So this is basically trying to compromise the integrity of the data output. So this is performed using DDHT, okay, data damage hardware Trojan. And all of these Trojans can be inserted at various levels of the design flow during the ML accelerator design. For example, it could be inserted at the scheduling phase. It could be inserted during the binding stage. It could be inserted during other stages like mux interconnect. The diagram on the right side here shows basically the internal structure of a machine learning accelerator. So you would have a Trojan trigger, okay, and this is basically the Trojan attack logic. The trigger signals are going to activate the respective Trojan logic here, or it could be internal Trojan activation as well. And the output of that would basically create the payload. And since this is the data path means the portion of the ML accelerator design that is responsible for data flow. It needs to be also controlled using a controller. So that's why you have a ML accelerator controller here. And the Trojan attack could be launched with the help of series of inverter chains. As you can see here, that this is the input. This input here is the input of this inverter chain. The output basically goes into another input, which is the vacant unutilized free port of our 8:1 multiplexer. So whenever an attacker spots that there is a vacant free port in one of the switching elements, it can actually misuse it by incorporating Trojan logic in that, like it has been shown in this particular diagram. And this part here basically is the Trojan trigger logic. Trojan trigger means it will trigger based on a specific rare event condition, or it could be time sensitive trigger. So in this case, it's a rare event condition where the preloaded constant k, when it becomes equal to this value of t, okay, then the Trojan signal gets activated and the final output will be produced from the multiplexer. Similar sort of a concept has been done for denial of service Trojans, where you can have a denial of service with the help of TSBs. Now, TSB stands for tri-state buffers. Tri-state buffers usually produce high impedance state, and this high impedance state means open circuit condition, where the ML accelerator would not be able to produce a respective output. Okay, so that sort of a configuration setup has been made here. And data damage would mean the output would produce a zero irrespective of whatever is the input. So in this case, the unutilized port could be connected to a ground value, as a result of which the output will not be generating the desired value or desired magnitude. Now let us talk about battery exhaustion hardware Trojan and how we can exploit it for CNN convolution layer. So this is a CNN convolution layer data flow graph, and as you can see, a fake pseudo operation has been inserted during the scheduling phase, okay, without exceeding the total number of resources. And as a result of which, because this is a multiplier and it has large power dissipation, so it is able to increase the overall power consumption of the accelerator. And such minor trivial modifications do not affect the overall design area because we are still using the same number of functional units. We are just trying to exploit or reuse the ideal functional units at different time instances of the scheduling phase. So triggering is a very important step in backdoor Trojans. So as I said, triggering can be of two different types. The first is when you can trigger a signal based on time sensitivity. Time sensitivity means that it is time induced Trojan. That means, whenever a certain time or clock cycles have elapsed, the Trojan will automatically get triggered. Technically, it is also known as time bomb trigger or time bomb Trojans, and they can affect the ML accelerators. The other kind of triggering is what we have shown in the previous slide, which basically exploits rare event condition or rare event triggering. So in the research community, there has been some attempts made on detecting such Trojans for ML accelerators as well as for regular accelerators. So these are some of those techniques where you can employ C2 RTL equivalence checking. You can also employ something known as DMR based security aware scheduling. You can employ side channel analysis, reverse engineering, path delay fingerprinting, GNN based and HLT based. All of these are published in the last 8 to 10 years. What this table shows is C2 RTL equivalence checking is very capable of detecting data damage hardware Trojan and battery exhaustion hardware Trojan, but it is unfortunately not able to detect PDHT and DOS-HT. The reason is in PDHT and DOS-HT, the models have to be available in C code. The Trojan models have to be available in C code, but not all Trojan attacks are available as C code. And since it's not available in C code, they cannot be directly analyzed using open source Bamboo tool, which is one of the tools that is often exploited to implement hardware Trojan and detect hardware Trojan. Now, HLT based, this basically tries to find out the number of operations after scheduling phase is over. Now, in case of battery exhaustion Trojan, we had employed use of fake operations which are integrated in the scheduling phase. So HLD would be able to find out if indeed the number of operations post scheduling is same as the number of operations, before Trojan insertion. So in case of this, battery exhaustion Trojan attack therefore becomes detectable in case of HLD based detection process. Now, if you try to analyze the ML accelerators in terms of design area, latency, and resources, what you will see is that we can do that in terms of gate count, design area in micrometer square, using a certain open source library. Like for example, it could be 50 nanometer library and so on. And in terms of the speed, which is a design latency in terms of nanosecond. And we can also see what is the Trojan power over it. Okay. Post integration of Trojan into the ML accelerators, from an attacker's perspective, the overhead has to be as minimal as possible. Okay. Because if there is too much overhead in terms of power and area, then the Trojan gets detected using side channel analysis. We also see that the overall gate count, okay, of the Trojan infected machine learning accelerator should not be high if it has to be evasive by nature. Okay, in order to be evasive by nature, it has to be it has to consume minimal number of gate counts so that it remains stealthy from the attacker's perspective. So in today's talk, we had discussed about the ML accelerators and its detection techniques, and we also had spoken about some tackling techniques to handle these ML accelerators. And my talk today was extracted from our recent research paper published in 2025. These are my references. Thank you, and I'm open to questions.
Dear participants, if you have any questions, you're free to ask now. See, this is the platform where we share our, the research works, our expertise, and it is a very good platform to ask question without any boundaries. So it's a very nice topic, that Trojan attack on machine learning accelerators. If you have any question, you may ask now. So rather, I do have one question. Can you
Sure.
enlighten some of the aspects in this field for beginner researchers?
Mhm.
Like how
So I
they
think
how do they proceed, or what should they learn about for doing these?
right. So basically, I think the starting point should be to know how to design a machine learning accelerator. I think that should be the starting point. And in order to know how to design a machine learning accelerator, I would recommend you to start learning about the different design phases. Okay, what are the different design paradigms used for machine learning accelerators? So one of the design paradigms which I had recommended in my talk today was using HLS framework, high level synthesis framework. If you recall, I have been speaking about high level synthesis. So high level synthesis is a very widely known or publicly available framework where you can read it from several sources to know how HLS works and how you can actually provide input in the form of machine learning algorithm to an HLS framework. And with the help of HLS framework, how you can design a machine learning accelerator. So that should be the starting point. The once the reader or once the beginner knows about the different stages of the design flow, then the next step would be to move into different kinds of attacks that are possible into that. Okay, so that is how I would start the person to start with.
Thank you so much, sir. Thank you for this wonderful lecture. I hope everyone got a better insight how to do work in this field. And thank you for being with us for this keynote session.
Thank you so much.
We are delighted to have you again. And just previous one, we had you in another conference, and
Right,
we
right, right.
are
It
so
was a
much.
privilege.
Yeah, thank you so much, sir. Thank you for sharing your thoughts. Our keynote speaker are with us and co-host as well. So we'll be starting. So, ladies and gentlemen, it is my privilege to a spin-out company from the University of Pisa, specializing in renewable energy and ICT solutions. Most recently, in 2025, Sir was awarded the prestigious Italian FIS2 grant for his groundbreaking project, New 4 MES, which advances structural neural network framework for autonomous system. Kindly join me to extend a warm welcome to the professor. Welcome, sir. We welcome you
Hello,
here.
hello. Good.
So, congratulations on your
Thank
achievement
you. Thank
recently.
you.
You may share, sir, your lecture. All over to you. Thank you.
I will gonna share the screen.
Yeah, sure, sir.
Okay. Okay. So I have already the presentation here. Okay. So I can start?
Yes, sir, sure.
Okay, thank you. Thank you.
Thank you.
So thank you very much to be here. Today I will gonna present Model-I, that is a framework for modeling design, for designing model structure and neural network for modeling, control, estimation of physical system. So I'm very proud to be here and to be part of this conference. I hope that we will enjoy this talk. So first of all, I want to give you a short overview of my presentation today. So I will start presenting a few slides about the NeoForMS project. Then I will show you the motivation that are bring me to write this project and design Model-I. Then some approaches, related works, and then we will go in deep in the Model-I framework, and at the end, some use cases. Okay, so the Neo4MES project is, I am a principal investigator of that project, and is founded by the Italian Ministry of University and Research in the 2003, but it will start in this October, and was founded for 1.2 million euros, so it's quite huge grant for Italy. Then the idea, the aim is develop a new approach to model and control physical system using model structural neural network. The principal outcome are Model-I, the framework, and a wiki website that will collect the knowledge that is that I built during the project. The case study are several autonomous systems, including drones, quadruped, and vehicles. But I want to stress the fact that the Model-I is a framework that is can be used for any mechanical system, any for model, any physical device. So these are only some example, but in general, you can apply this framework your problem if you have something that is related to physics. So in the end of the slide, you have a link if you want to get more detail about the project and of my career. Okay, so I go straight to the motivation why model structure and neural network are so important. So if you start to think about the neuron, the perceptron is a very simple mathematical object that have a sum of inputs and then a nonlinear function. But of course, using a single perceptron, you can model so much things. So what you need to do is create a cascade of those those layers, those neurons, in order to identify a specific nonlinear function. There is a theorem that is called the universal approximation theorem that say a neural network with a single hidden layer can approximate any continuous function. But I want to show you an example, very simple example of this. So if you want to cluster points, you can see that a simple network, in this case, I have got some trouble again to identify, but commonly when you have a simple cluster, it's easy to identify with a two layer. But if you have a more complex structure like this, the network can struggle to find a good solution. But easily adding, for example, the sine and the cosine of the inputs, the network working a bit can much easier identify the two cluster also in this strange case. What I did, I just compute the sine and the cosine of my inputs. So I structure the network. I put some information inside my network. So the idea is something that is very similar to what in common the scientific community does. So for example, computer vision, speech recognition, data generation, or natural language processing are common taken using a specific structure for the network. So convolutional neural networks, long short-term memory, generative adversarial network, transformers, that the one thanks to the which we now have ChatGPT. So without transformer, it will be impossible to create such networks. So it's important to understand that structure in the network is fundamental to get some specific result. So why we not create a specific network or a bench of possible structure for the network for identify, model and control mechanical system? So this is the idea. So in general, when you want to model and control system, you can use two approaches. So you have two different approaches. From one side, you have the model-based approach. The model-based approach commonly leverage physics knowledge, use equation-based formulation, but on the downside are that it's difficult to model everything. And also the system identification may require ad hoc experiments. So maybe you need some experiment specific to identify specific characteristic of your mechanical system. On the other side, you have the data-driven approach, pure data-driven approach, that not need of an expert knowledge. The function that you identify can be very complex, but the downside is a black box structure. You need a lot of data for training and also can have a pure generalization. The idea is combine these two approaches in one single object that is called model structure neural network. This network can be flexible in the flexibility, so we take the flexibility of data-driven approach, but also embed the domain-specific knowledge into neural network internal structure, increasing explainability because we know what is the meaning of the single weight inside the network, and also helps the generalization of the network. Okay, so I'm going to present some motivation, the approaches. So how you can structure a neural network. There is several ways. So one is decide on the problem. So you can shape your problem, changing the input, the output, thinking what can be the good input, what input can be removed to avoid that the network learns something that is wrong. You can curate your data, so you can modify and apply some function before the training on your data. You can design an internal structure, as we did. So in particular, the framework works on this point, so design the internal structure of the network. You can design the loss function, so shaping the loss function in order to fit your function, what you need to have, or design an optimization algorithm. So changing the optimization algorithm to fit better your function. Okay, so some related works that start on this idea. So the scientific community is already working on structure the network. One very famous approach is called the physics-informed neural network, or PINS, that is come in 2019 from Raisi. And what is did here, he used those networks for identify and integrate partial differential equation. But here the main idea was to structure the loss function. So the network that is used for integrate this partial differential equation is an unstructured neural network, but what it was structured was only the loss function. So it's different from our approach. Another approaches that comes from the PINS, from from the application of the structure in the loss function is the Hamiltonian, the Lagrangian neural network, also some network that mimic the Pontryagin principle for optimal control problem, and also for dynamic, and also using dynamic programming. So these are other approaches that still working on structuring the loss function, not the neural network. Another possible approach can be the possibility to combine the use of non-structured neural network with an analytical model. So you have an analytical model, you fit the parameter of your analytical model, and then you add the neural network to get what was missing in your analytical model, and you compensate the effect in order to get a better fitting. But still, the neural network is unstructured, and then you have a standard analytical model on the other side. So you just combine the two way, but you not really integrate the idea of the network and the structure. So instead, in our approach, what we are doing is really structure the neural network. So we really think, we really identify and build specific layers of the neural network that are able to better fit our model, our system. So for example, we have many very good results on vehicle dynamics, vehicle estimation, and general model mechanical system or control mechanical system. But these are only preliminary results because the project is started now. What I did so far is just collecting what I did, and but I'm not really start to work on that. So I would like to expand the fields of using these approaches in many different fields. So I'm very happy to share with you this new possibility. So, okay, so this was the approach. So the approach is integrate and write specific layer for the neural network and try to find these new layers that are better fitting your system. Okay, so now we move and we go in deep in the modeling framework. So the idea is the motivation. The motivation are modeling and control estimation physical system. So this is the objective. Model, control, and estimation physical system. Whose internal dynamics may be partially unknown, but this is very common. No? When you want to take into account friction are very difficult to model, or many other stuff that are very common. If you have backslash, that zone in your system, it's hard to model this stuff using standard modeling. Instead, using neural network, using the data-driven approach, it's easy to take into account. Speed up the development of non-model structured neural network, because I not explained, but writing model structured neural network with a standard deep learning framework can be very hard. It's very hard to shape the network without a very good understanding of deep learning. But if you have a scientist that are really familiar on your field, it's difficult that you are also a very a good designer of neural network. So Modeleye try to help the scientist to speed up the process of developing model structure and neural network. Commonly, the code from standard deep learning framework is reduced by the 75%. So the second thing is support professionals with classical modeling background, such physicists, engineer, using data-driven approaching by embedding knowledge inside to address their challenge. And this is very important because it avoids the common mistake of using standard deep learning framework that can be, for example, the shaping the dimension of the tensor or writing some specific loop inside the network that can be hard. So there is a lot of stuff that are common difficult to design in a standard deep learning framework. If you want to try to design model structure in a network, Modeleye can be a very good way. And the last things, I want to try to write a repository of incremental know-how that efficiently collect approaches with the same purpose, that are building an increasingly advanced library of model structure and neural network for various applications. So the idea is we have a model eye that will try to collect layers for specific problem and integrate in one single framework. And then when you have a different problem, you can try to apply those layers in your field. Okay, so just to explain the workflow, the main workflow of Model I. Model I is cover all the pipeline of modeling. If you want to see more detail, you can go in the website. Is a Model I, I'm not say, but is a completely open source software in GitHub, so you can scan the QR code and look the code. And now it's already working for specific problems. So we start from designing a neural model definition. Then this model definition define a neural model. This neural model can be combined together with other models. And then using another part of the software to help you to create the dataset, you can combine the dataset and the model to train the network. Then the trained model can be validated. Also, the validation is covered by Modely because when you want to apply a deep learning technique to a different field, commonly you want to set and check different stuff to common standard evaluation that you can do in deep learning. So, for example, in mechanics, we are commonly use spectral analysis to see if we model correctly a system. We integrate such evaluation inside Modely. So easily you can test your spectral, you can make a spectral analysis of your model to verify if the model learned correctly. Then the validated model can be combined again for adding another pieces because Modely can combine different networks together to create a whole network. So you, for example, if you have a car, you can model the engine, you can model the friction of the wheel, you can model the aerodynamics with different networks, and then you can combine all together to get a whole model of the vehicle. Then you can export a network, and the network can be exported in standard PyTorch and ONNX format. Okay, so the basic principle, the model structural neural network embeds and generalize physical principle and prior knowledge where the parameters are learned from experimental data. So now I will want to present the main ideas that we already put inside the Modely framework. So commonly we apply the superimposition of forces. That is a very typical way to tackle forces for a rigid body. You use finite impulse response filter and infinite impulse response filter to take into account dynamics, so all the dynamics of the system. You use local models and custom function to take into account nonlinearities. And also we capture residual of analytical model through ad hoc generalization. So when you have a specific problem, so friction delays, you can build a specific layer to put inside this layer inside your network. Embedding easily the concept of time inside your neural network. The time is not something that is common defined in a standard neural network, but for Modely, the time is something that is very easy to manage. And the last things is flexible managing of recursive networks. So you can easily create loops or connecting different networks together to create a whole neural network. Okay, so now I'm gonna move to the use cases. I will wanna present some results that during my career I obtained using Model I. Okay, first of all, I want to start from a very simple example of learning model and control of a system because the idea of Model I is starting from learning a model of the system, and then after we learn the model, we can learn the controller thanks to the model we learned at the step before. I make a very simple example that I hope that you understand if you're not familiar with mechanical system, but I think this can be very, very simple system. So this is a mass spring damper system. So you have this mass, you have a spring, a damping, and you apply a force, and you want to reconstruct the dynamics of this system. You doesn't know about the stiffness, the damping, and the mass. So commonly, the mathematics, the equation of the motion of a mass spring damper is the one you can see on the right side of the slide. And on the downside, there is the neuralization of this mass spring damper equation. So we apply a finite teaspoons response filter that is mimic the discrete dynamics of the mass spring damper system. So the idea is we start from the continuous relation, continuous equation that represented the dynamics on the right side. We discretize the relation. We obtain this new definition.
Society, Paris, France. Dr. Kerr holds a PhD and her research expertise lies in computer vision and machine learning, with remarkable applications in bioimaging, brain imaging, and digital histopathology. Her work has garnered significant international recognition with nearly 750 citations reflecting the impact of her scholarly contributions. She is widely respected in the academic community with the Edge Index of 12 and I-10 Index of 15, demonstrating the depth and influence of her research. Today, she will be sharing her insights on the theme towards an artificial intelligence framework for veterinary health diagnosis and clinical automation. Please join to extend a warm welcome to Dr. Anuradha Kar.
Is in full screen mode. Okay, so if it's okay, I can start.
Yes, ma'am, over to you.
Thank you very much. Okay, so good afternoon, everyone, to the participants in India, and I'm actually in Paris at the moment where it is still morning. So first of all, thank you very much to Chitkara University for this invitation to present this keynote talk. So this is, I will be speaking on the topic of towards an artificial intelligence framework for veterinary health diagnostics and clinical automation. So as Dr. Viva already introduced me, so I would probably just go rapidly through my profile. So I'm an associate professor in AI and robotics at Ivan City. This is an engineering institute specializing in AI and data science, absolutely at the heart of Paris in France. And my research areas focus on deep learning, computer vision, explainable AI, AI for health, and my research focus is also in the field of generative AI and AI for ethical purposes for the society. So today, the title or the subject of my talk is the development of an artificial intelligence framework for veterinary health diagnostics and for clinical automation. So this is an overview of what I will be covering. So I will be talking about the growing demand for healthcare for pets. Normally, we focus on healthcare for humans, but I will discuss how pet healthcare, that is our companion animals, the welfare of those companion animals, how they're being focused or highlighted at the moment globally. And then that has given rise to a need for reliable, fast, and accessible pet health diagnostic technologies, and as well as some challenges. And this is where I will be presenting our solution, research that we are doing in collaboration with our faculty members and students at Ivan City. So this is the framework actually we are developing, and this is something I will be presenting during this talk. So I would like to start with an introduction about the pet health scenario. That is, pets are very dear to us. They are almost as close as members of our family. And at the moment, globally, the number of pet owners is pretty high in different countries. For example, in the US, 66% of the households have pets. This could be cats, dogs, or any other animal. In Europe, it is 46%, in China, 50%, and also in India, it is currently 10%. But there is an increasing trend in the number of pet ownerships. That is, more and more households or people are adopting different pet animals. So this has been sent as a result of a census where it has shown that this is an upper, like growing trend in every country. That is, the number of pets in households are increasing, including India, including US, in different countries. So as the pet ownership and care becomes prioritized, because so many households are having this kind of pets, companion animals with us, so this has also increased the demands of professional veterinary services. So this has led to the development of clinics, hospitals, And like before, these clinics used to be mainly focused in the big cities, but as the ownership number is growing, these pet clinics and hospitals are spreading to the urban areas or semi-urban regions as well. So as a result of this, there is a very strong need for specialized diagnostic instruments, technologies, and trained veterinarians all over the world. So, and this is also seen in this trend, upgrowing trend in the like animal diagnostic market size. That is the number of pet products that are related to pet health, pet diagnostics. They are growing. They are growing, and it's quite like obvious in different countries, as is seen in this curve or the plot as we see here throughout the year, starting from 2023, and it is projected to grow until 20 in the next 10 years. It is only projected to grow. So, for example, the number of veterinary clinics in the US, where I showed you the pet ownership is as high as 66%. Currently, there are around 28 to 30,000 clinics, pet clinics there are. And in similar way in Canada, the number of pet clinical, I would say, practices or these clinical centers is increasing. So they have increased from 3,800 to 4,800. So almost 1,000 clinics has increased within 3 years. So this is just to support the statement that pet healthcare is growing. The need for good facilities for pet healthcare is growing all over the world, as well as there is this increased awareness in towards the health of pets. So basically, like, what does keeping a pet involve? So it is as much as it gives us love and care, and we also should be replicating that or responding to those pets with adequate care, and especially related to their health. So there is a census on global veterinary diagnostic testing market, and it shows that the amount of testing or diagnosis or diagnostic facilities required is much higher for companion animals compared to other types of animals. That is something we call livestock. Livestock includes the cow, sheep, goats, something that are helpful in our agricultural practices. But the amount of diagnostic testing that is required for our companion animals, that is pets, it is higher. And this is a census that shows that how much more these veterinary clinics are becoming more important. Now, as like the pet in ownership increases, similarly, as I said, that one major component of keeping a pet is to care for its health. Because one of the reasons is that pets cannot take care of themselves. So it is the pet owner's responsibility to help the pets maintain a good health. And so, as the number of pets are increasing, similarly, the awareness about pet health is also increasing, which actually has led like a global awareness on the types and number of pet illnesses that currently occur. So some of the most commonly reported illnesses in the most common pet animal, which are the dogs, also cats, of course, but some of the common types of pet illnesses that are seen all over the world include cardiovascular diseases. That is something related to the heart of the pet animal. Then there are the virus, cancer, rabies, heartworm, calf ringworm, and diabetes. So these are some of the different illnesses that commonly affect our pet companions. And veterinarians noted that most of, at like a huge percentage of these diseases are actually coming from the cardiovascular ailments. That is something related to the heart. And actually, these are the diseases that lead to fatality. So maybe some other diseases like ringworm, and then like I would say insects, heartworm, these can be cured. But the diseases related to the cardiac functions of the pets, they often like go directly towards a pet fatality, something that no pet owner wants. Um, so sorry about the message over here. Um, so, um, so veterinary healthcare, similar to the number of like increase in the number of pets, it faces several challenges. Like as I said, the market for pet healthcare is increasing. The number of pet owners are increasing. At the same time, there are some pressing challenges that we see in global veterinary healthcare. So it starts with the factor that the number of pets is increasing rapidly, but the number of trained veterinarians who are available to treat these pets is not increasing in a proportionate rate. This is the first problem that the pet world or pet veterinary world is facing. That is, there are not enough doctors to treat these animals, although the number of animals we are keeping is increasing. This this results in the shortage of healthcare professionals for the pets, and which actually accumulates. That is, so there are shortage of like professionals, which leads to more stress for the existing professionals. That is, when once the pet volume increases, the number of patients increases, it increases the stress on the existing veterinarians, and the result of which is that the quality of diagnosis decreases. That is because with more stress, more volume of patients, this leads to burnout in the veterinarians. What do the veterinarians do? So they are the people. So this is to give context about what are the functions of a veterinary doctor, because our framework is, as I will show you in a later slide, that is, our framework is aimed to help or aid these veterinarians actually in clinics. So what does a veterinarian do? So they are responsible to provide care to healthy and sick animals, mostly pets, or they could be also for livestock, but in our case we are only talking about the pet or companion animals. So they give wellness exams, vaccinations, and surgeries. They perform exams, radiographs, and interpret blood work, and then they discuss the next step with the patient, with the pet clients or the pet parents, and provide treatment. So they have to go through a full workflow of doing the diagnosis, doing the tests, then getting the results, doing the interpretation. So the full workflow for all the pets that they receive, all the patients that they receive during a period of time, they have to do the whole workflow. So a veterinarian's responsibility is quite high. So, as I said, the current challenge is the shortage of veterinarians in the clinics. Although the number of clinics are increasing due to the demand from the pet owners, the number of veterinarians cannot keep up with that pace. So, not all clinics have access to specialist radiologists. So, pet radiology is actually one of the main diagnostic techniques for detecting many diseases. But there is a shortage of the specialist radiologists, that is, the veterinarians who are trained to interpret PET X-ray. So radiology means X-ray imaging mainly. Now there could be other modalities, but X-ray is the most common form of veterinary imaging. So there is a shortage of trained professionals who can interpret the PET radiology data sets. So these factors are creating a pressing need for solutions that can support these veterinary clinics, automate repetitive tasks, and improve efficiency. So the whole idea about this addressing this challenge is to develop new tools that can help the veterinarians to reduce their workload, at the same time provide accurate and reliable results for the pets, so that they can be rapidly diagnosed if there is any problem happening in their health, and they can be treated. So these are again some census that have been done on veterinarians, which says that 40% of veterinarians say that time management is a challenge because they receive a huge volume of pets and the pets cannot complain about their condition. Detecting their diseases is more critical than detecting a disease from a human patient. So, and then it needs more time, more involvement from the veterinarians, which puts pressure on their time schedule. And secondly, there is overload of administrative work. So not only the veterinarians have to do the clinical work and the clinical diagnosis, they have to also do the administrative paperwork of generating, interpreting clinical reports. And there is a problem over here. That is, there is overload in both this type of workload on the veterinarians. Now, let's come to one kind of pet illness, because this is also the focus of our framework. So, as I told you, there could be different kinds of illnesses, including rabies, cancer, worms, as well as there is one majority of diseases that come from the heart like ailments. So, one of this kind of disease is called dilated cardiomyopathy, or DCM. So DCM is one of the most common heart diseases in large breed dogs. So what happens in this kind of disease is that the dog's heart becomes enlarged as the heart muscle weakens and becomes thinner and stretched out. So this figure over here shows you what a healthy heart of a dog patient looks like, and what happens if it gets this dilated cardiomyopathy. That is a whole heart chamber kind of, it increases in dimension. So it is usually a result of an underlying cardiac disease that shows up in this format, that is the heart enlarges, and it affects the heart structure as well as the functionality. When the heart enlarges, it encounters several problems. For example, its ability to pump blood and perform essential functions. As you know, like from human cardiology, any problem of the heart directly affects the living condition or even leads to fatality. It's the same case for pet animals. So in dogs that have this dilated cardiomyopathy or DCM, their ventricles start to wear down and become thin and weak. Okay, so basically there is a big change in the structure of the heart, and that actually like shows up as different disease symptoms within the pet. That is, for example, it becomes more difficult for the pet heart to pump the blood, and then there are symptoms, for example, cough, breathing problems. Even the pet can collapse. There could be some like abnormal swelling shown. Then there is less tolerance to. Basically, the animal becomes very fatigued. Then there are some external conditions like cough and breathing, but at the same time this condition develops very slowly, and sometimes it gets unnoticed until the like pet really collapses, where nothing more can be done. So this is basically when DCM leads to congestive heart failure, which is actually a terminal condition, and the pet passes away. So how do we detect this kind of disease in dogs? I'm especially going towards the dogs because again I'm going more towards our framework. Again, this cardiomyopathy can happen in other animals like cats, but since our research is focused mainly on like data from dog patients, I'm slowly orienting my talk towards the conditions that are seen in dogs and how they are identified. How do we detect cardiomyopathy in dogs? So the clinical signs, as I told you, it shows up as different symptoms. For example, the dog doesn't want to exercise anymore. It loses energy. It is, I would say, like there is possibility of collapsing. Then there is coughing. Then there are some heart issues like arrhythmias. And it is like the problematic part is that it is often silent until it goes to a very advanced stage, which is the most challenging part of this disease. The diagnostic tools that are used to detect this kind of heart enlargement or cardiomyopathy are these include electrocardiogram or ECG. Then there is echocardiography. It is again one of the popular tools. And finally, thoracic radiographs, that is chest X-rays. Okay, so there is a sample of a chest X-ray from a dog patient, that is as you see on the slide. So on the left side, on the figure A, you see a dog with a normal sized heart. Okay, and in the figure B, you see when the heart size has expanded due to this condition of cardiomyopathy. And this is visible in this kind of lateral thoracic X-rays or radiographs. This is very easily visible, but then this has to be diagnosed early enough that the disease hasn't advanced very much. Otherwise, there is possibility of fatality. So this is a metric which is used to estimate the presence of this disease of cardiomyopathy, which is called the vertebral heart score. Again, why am I introducing this? Because this is the metric we are actually using in our framework, which I will introduce to you in a minute. So this is a vertebral heart score or VHS, which is a number that normalizes. So basically, this is an indicator of the heart enlargement, how much the heart has expanded from its like normal state to when some pet has cardiomyopathy. So how it is done, it is a bit of a mathematical procedure. Here in the figure, you see the structure of the vertebrae. Like what you saw on the previous slide from the X-ray, it is something that is shown as a diagram over here. On top, you see these are the vertebrae of the dog, and there is a particular vertebra which is of interest, which is the fourth vertebra, which is mentioned as T4 in the figure. And then there is a heart as seen in the chest radiograph as you saw in the previous slide. So what is done is that to understand how much the heart has enlarged because of the disease, the two parameters from the heart are measured, which is the two axes, that is the long and short axis of the heart, because you can roughly estimate the heart shape as an ellipse. So it has a long and a short axis, and these two measurements are very vital to estimate how much the heart has expanded. So what is done in the vertebral heart score metric is that these two measurements, that is a long and short axis of the heart, are projected on the vertebral axis. And then the sizes, the long and short axis sizes, are measured in terms of vertebral count. So this is how we get, I have shown a brief description over here. On the figure, you can see, now this is an established clinical procedure that has been developed over the years. And it is one of the most standard procedures to estimate if the heart has expanded. So the heart size is projected on the vertebral axis. So for example, so basically this is the count of how many vertebra is covered by the length of the heart. That is a long axis and the short axis. And that unit actually should vary between 8.5 to 10.5. It is if this VHS score stays between this limit, we say that the heart is actually it has an okay condition. It is under normal condition. Whereas if this VHS score goes above 10.5, we say that the pet is experiencing a cardiomegaly, which means an expansion of the heart. So, what is the advantage of this metric? This metric actually is very central to our framework. That's why I'm taking you through the definition of this metric. So, what are the advantages of using this metric? It is very simple, quick, and inexpensive to measure, because a heart is a 3D structure. So, unless you have a 3D imaging technique, it is very difficult to understand its size or structure variations. However, with this VHS metric, we can very easily, just from a lateral X-ray, we can estimate the size variation of the pet heart. And it provides a quantitative measure of the cardiac size. That is, you can actually see whether the heart has increased in size or it is normal. And it helps to track changes over time. So if you have the VHS metric taken regularly for a patient, for a pet patient, you can see its variation over time. Maybe whenever the pet gets an X-ray, maybe once a year or twice a year, you can actually see how much the heart, whether the size of the heart is changing or not. That helps to keep track of the pet health in terms of its cardiac status. Disadvantage is that the first disadvantage is that so usually in clinics, since as I told you this is a standard clinical practice, usually it is done manually by radiologists in clinics. Okay, they take a pet X-ray, chest X-ray, and they estimate this parameter of VHS, but manually. So the clinicians or the radiologists have to measure this size of the heart and convert it into VHS manually. And that actually leads to very, there could be errors due to human estimation. As we know, in any clinical practice, there are human errors. Similarly, this affects this VHS estimation to a large extent. And as I told you, because of this pressing need for veterinarians, because they don't have time, they are very much loaded with work, this estimation goes frequently wrong. And that, as you can imagine, that can lead to a wrong diagnosis. So this is one of the main problems of this VHS estimation. That is, it needs, first of all, trained and skilled veterinarians. And number two, it is very, I would say, like intensive. It can lead to interpretation errors depending on the skill and the workload of the veterinarian. So this is one of the main problems. And then there are other errors. For example, the pets, they can have positioning errors, because depending on how they were positioned during the X-ray, there could be problems in the X-ray image. And also it cannot distinguish between different causes of cardiomegaly. Like, it just gives you the idea whether the heart has enlarged. It doesn't give you an underlying reason of why it is happening. So this main takeaway from this is that the VHS is the main metric for estimating the heart disease of pets. However, the manual estimation of VHS is not the best practice, because it can include human errors due to lack of trained veterinarians and their workload. So this is where our solution comes in. These are some members from our institute who are working on this solution we are proposing, a framework. So this is a deep learning based VHS estimation and automatic clinical report generation pipeline. This is our focus of research. And so these are some of our students from our final year of masters at Ivan City. And these are some of the faculty members, including me, who are working on this topic to develop this framework. I will just take you through the framework after this. So this is our workflow using deep learning in two aspects, as I will tell you. So what are these parts of this workflow? So firstly, there is data. Of course, the data is the radiology data, as I showed you. So these are X-ray images in DICOM formats, like standard radiology formats. From there, what we are doing is we are extracting the heart region from the PET chest radiology. Then we are extracting the vertebra. That is, as you saw, like to estimate the VHS, we need the vertebra locations. That is a T4 vertebra location we need. So once we use these two parameters, that is the heart location and the size and the vertebra location, then we are using it to estimate automatically the VHS. So there is no manual radiologist effort required. Once you just have the chest radiology report or the radiology image, our algorithm will be able to extract the heart region, extract the vertebra location, and estimate the VHS automatically. And not only that, we will be generating a report, a clinical report based on the VHS values, to say whether the patient, the dog patient, is healthy or not. So this is our entire workflow. So it contains the several components. So first is data processing. That is, we have a data processing pipeline initially, which applies different image normalization and augmentation techniques. For the audience who are familiar with computer vision, you know these are very standard practices to apply any deep learning model to an image dataset, that is perform image normalization and data augmentation. Then we have two deep learning modules for one is the heart segmentation, that is, as you saw the radiology images, the heart actually occupies a space within it which needs to be extracted. So for this we are using an UNet model for segmenting the heart region, and then we are using a YOLO model to extract the vertebral locations. Finally, after we extract the heart and vertebra, we are estimating the VHS values, and then we are using this information, that is a VHS value, the information from the chest radiology, for example, the metadata from the radiology image, to create a complete clinical report. So this is the raw data set that we have. So it is taken from the Hospital Universitario Virgen de la Arixaca. It is from Spain. So it is coming from a Spanish hospital. And actually we received like big size data sets, but we observed a lot of variability in the PET radiology data, as we can imagine, because they are more mobile than human patients. So there's a lot of anomalies in the data set. So out of a set of 1,000 images that we received, we could only take 191 images that were suitable for deep learning purposes. Then we actually, so these images came unannotated. So we had to annotate the heart and vertebra regions. So we use a platform called RoboFlow, which allows annotation or demarcation of the heart and vertebra locations. So using these images, this is a snapshot from the RoboFlow platform where we actually delineated or marked the heart and the vertebral locations, which will be used in the next step for the deep learning based heart and vertebral localization. And then these are some of the data pre-processing steps that were used, that is resizing. So one problem with, again, PET radiology is that the data sets are highly variable. There is no constant quality, there is difference in intensity, there is difference in structures, because PETs are mobile and clinical data is always having this kind of quality issues. So we face that as well. But we implemented this pre-processing pipeline of image standardization, data augmentation. So as I showed you, the number of images that we could finally use was quite small because we had to filter out much of the data. So we applied several types of data augmentation like flipping, rotation, scaling, contrast adjustment, like that. And finally, we improved the quality of the available radiology data with the histogram equalization. And to increase the variability in the data set and simulate real life conditions, we also added variable quantities of noise in the images. So this is our first step of extracting the heart region from the PET radiology images, as you can see in the image here. So for this, we use a UNet model, again, for computer vision researchers in the audience. This is a very, I would say, mostly used, very popular segmentation, image segmentation model. So what we do here is that with the input image over here, you see is a chest radiology image of a PET, where you can see the bones and the heart inside the rib cage. And this model, this UNet model, is successfully extracting the heart region from this image, which we can actually superpose and check that it actually can do the heart segmentation with a high degree of accuracy. So the next step after we extract the heart region is the vertebra segmentation, because we also need to know the locations of the vertebra to calculate the VHS. For this, we are using the YOLO model. The YOLO is an object detection model, a highly popular object detection model. In our case, we actually detected the four vertebra, T1 to T4. So we actually annotated these images, these vertebral locations in the initial data set. And using YOLO, we could detect these with accuracy of around 75%. That is, we could identify these vertebral locations with this model. So the next step, once we had this information about the heart location, heart size, and the vertebral location, finally we could calculate the full VHS values. So this is basically a bit of the theory of how the VHS was calculated using the heart diameters and projecting them on the vertebral axis. And so these are some of the sample results that we got. That is, for example, for this image on the left, the ground truth was 11.22 and our predicted VHS. So as you can see, it is a completely automated pipeline without requiring any clinician support. So I will go rapidly through it. I know I'm a bit behind on time. So as I can show you that we achieved actually quite high accuracy in estimation of the vertebral heart score based on our completely automated pipeline. The next step was to have this application which could take in, this is also part of our development, that is, this is like a dashboard which takes in radiology images and automatically generates the VHS score. So the clinician, if they are using our framework, they can just upload radiology images and get a vertebral heart score using the algorithm that we developed. So it is like a complete platform. And finally, this is the report generation part, that is using the VHS code that we calculated using the deep learning models. Our framework also generates a complete veterinary medical report. For this, we are using the support of generative AI, that is the LLMs like Olama or GPT, which can be used in conjunction with the VHS measurements we are doing, and as well as some metadata taken from the DICOM images, and now we are generating. So this is actually to help the clinicians through the entire workflow. They just have to upload a radiology image and they will instantly, as we saw, like the total process takes around 4 to 5 seconds. Within 5 seconds, they will get a complete medical report with the VHS estimate. So this is just intended to help the veterinarians in their work. I will rapidly conclude. So why do we need artificial intelligence in veterinary diagnostics? Because firstly, the veterinarian shortage, because of which we need this kind of clinical automation, that is automating these clinical workflows. Then there is rising demand from the pet world because the number of patients are increasing. We need more accurate results and more fast results. So the ethical challenges that can come up in this kind of work is whether we can trust the AI systems. This is always an ongoing question in AI application in health. That is whether we trust AI models and whether they are coming with some sort of bias, or they are influencing the fairness of the model. So there are some of these ethical challenges also are there. With respect to our project is still ongoing, and as I showed you some preliminary results, and we are still trying to improve these VHS estimation to make it more ready for clinical use, and maybe in future, if possible, to integrate with an actual veterinary practice software. So thank you very much. I hope I haven't exceeded my time limit. And thank
Just
you
few
once
seconds,
again.
that's fine. Thank you, ma'am. Thank you so much for being with us, because it's a lot of work that you have shown to us, which is very, precious for a researcher to show her work like that. So it's been so wonderful by visualizing your work. It is so nice that you're doing this so much nice work. Thank you